Oxidation Reduction, Lecture 3. Now, here's your table. The left side is filled out, but we're going to take it one item at a time. Let's start with the perchlorate radical. Now, the perchlorate radical has oxygen with a -2, and what is the charge on chlorine? It's +7. Can it act as an oxidizing agent? Can it gain electrons? And the answer is yes, it can. The chlorine can gain electrons. Well, when it gains electrons, what does it change to? Well, it can change to the chlorine can gain electrons, and it can change to the chlorate radical or the chlorite radical or the hypochlorite radical or chloride or chlorine. There are a lot of things it can change to. Well, can the ClO4 minus, the perchlorate radical, act as a reducing agent? In other words, can it lose some more electrons? Remember, don't count oxygen in this now. And the answer is nope, nothing that we would recognize. All right, look at this. How about the element magnesium? Will the element magnesium gain electrons? Well, have you ever seen magnesium with a negative charge? So not in the common things that you know. Well, what about as a reducing agent? In other words, will magnesium lose electrons? Yeah, there it is, magnesium with a +2. Okay. How about hydrogen peroxide? Oh. Now here you have hydrogen peroxide, and oxygen has a -1 charge. Can it act as an oxidizing agent? Can it gain electrons? Oh yes, it can go to oxygen with a -2 charge in either water or hydroxide ion. Well, what about its product as a reducing agent? Can it lose electrons? Can the oxygen in peroxide, which is a -1, lose electrons? And the answer is sure. It can form O2. Are you getting the idea? Let's go to another radical. Let's look at dichromate, Cr2O7, -2. Stop for a minute and figure the oxidation states of things here. And the oxidation state of oxygen is -2. And what about the chromium? It's a +6. Can chromium gain electrons? At +6, can it gain electrons? And the answer is yes, it can. And it can form things like the chromic ion, the chromous ion, or chromium in the elemental state. Well, can chromium at a +6 lose electrons? And you will say, not that I know of. All right. Let's go to a compound. Let's look at manganese dioxide. Oxygen's a -2 there, and what's manganese? It's a +4. Can manganese gain electrons? It's a +4. Can it gain them? Yes, it can go to manganese ion or manganic ion, either one. Can manganese at a +4 lose electrons? Think about your range of oxidation states. And the answer is yes, it can. It can go to a +7, like in permanganate. If you need to catch up, then pause your video for a moment. Let's look at the nitrate radical. Here you have oxygen with a -2 and nitrogen with a +5. Nitrogen with a +5. Can it gain electrons? Yes, there are lots of things. Lots of these different compounds. Lots of these different structures. And of course, there's such things as the NO2 radical. There are several things it can produce as an oxidizing agent. Well, what about when nitrate acts as a reducing agent? Can it act as a reducing agent? Can it lose more electrons? Not in the common sense of things, not in the common state of things. Okay? How about this element, chromium? Can chromium act as an oxidizing agent? Can it gain electrons? Not that you know of. Can it lose electrons? Oh, yeah. Can you think of something? Do I have it in the list? There are other things too. Besides these I have, there's dichromate, for example. What about iodine? Can iodine act as an oxidizing agent? In other words, can iodine gain electrons? You say, sure, it can form an iodide ion. Can iodine act as a reducing agent? Can it lose electrons? Oh, yeah. It can form those oxides that you form, those radicals. Yeah, those are all has positive charges in those. What about an old friend, the ferrous ion? Can the ferrous ion act as an oxidizing agent? Can it gain electrons? The answer is yes, it can, and when it does, it can form Fe0. Well, can it act as a reducing agent? Can Fe plus 2 lose electrons? Sure, it can form the ferric ion, and for example, it could form Fe2O3, in which you have a plus 3 charge for the iron. The iodate radical. Oxygen's a negative 2. What's iodine here? That's right, it's a positive 5. What can it form? It can form iodine or the iodide ion. So it can gain electrons and form either of these, for example. These are not necessarily all-inclusive. What can it form if it were a reducing agent? If it were a reducing agent and lost electrons, what could it form? How about IO4 with a negative charge, in which iodine has a plus 7? Have the idea? Was this a good exercise? These are not things necessarily for you to memorize. These are just things to help direct you in your way of looking at the ability of various compounds or elements or radicals or whatever to perform as oxidizing agents. Now we're ready to look at voltaic cells. Voltaic cells. Just what is a voltaic cell? Well, a voltaic cell is a spontaneous oxidation reduction reaction that, when it occurs, can produce an electrical current. Now, you remember this, don't you? Remember the activity series? There it is. Do you recall how it works? Do you recall that an element replaces an ion below the element? Well, we're going to look at that in a way, but we're going to look at it in terms of half cells. Let's look at the all-important Daniell cell, the zinc copper ion cell. Look at this reaction. You have zinc plus cupric sulfate giving you zinc sulfate and a precipitating copper. This is done in solution. Now, when we write this as a net ionic equation, we have this. We have zinc plus the copper ion producing the zinc ion plus copper element. When we do this in half cells, oxidizing half cells and reducing half cells, the reduction half cell has zinc going to zinc ion plus 2 electrons. And copper in the other half cell gains 2 electrons and produces elemental copper. But here's how it's going to look. We have cupric sulfate, we have a zinc bar and a beaker. We take the copper sulfate, cupric sulfate, and we put it into a beaker, and we put in our zinc bar. And notice, it almost immediately changes colors. You almost immediately are getting precipitation of some kind forming on that zinc bar. And if we leave it sit for a while, then we find quite a large deposit. And notice the blue color is getting lighter in that solution, because the copper ion is coming out of it and precipitating as elemental copper all along that zinc plate. Zinc is forming zinc ions plus 2 electrons. The cupric ion from the copper sulfate is picking up those 2 electrons and forming copper metal, so that our overall reaction is zinc metal plus copper ion forming zinc ion plus copper metal. Now, how can we use that and make it provide electricity for us? Well, we can do it on something sort of like the dry cell battery. Now, this doesn't use the same exact reactions that we're talking about, but it is the same kind of a process. In a dry cell battery, you've got a carbon rod going down through the center of it. Reduction occurs in that carbon rod. You've got a zinc cylinder, and oxidation occurs in that zinc cylinder. And that carbon rod and the zinc cylinder don't touch each other. All that packing material inside is something that is able to conduct an electrical current. Now, take that and you attach it to something like your calculator. You've separated the half cells, but you have allowed the electrons to flow. You can get a complete circuit and power your calculator. And that is the basics of the way that a dry cell battery works. Let's look at it now when we separate the two. On the left, we have a solution of zinc sulfate with a zinc plate in it. On the right, we have a plate of copper or a copper strip, and we have that in a cupric sulfate solution, that blue solution. Now, what is going to happen with this? We have a salt bridge that connects the two here, and a voltmeter here that's able to read the current when electrons flow through. Here's the way it's going to work now. The zinc is going to lose electrons, and when it loses the electrons are going to flow over through to the other side, where the copper is going to pick them up. Now, when the copper ion picks up those electrons, you have a deficiency of negative charge on the left and a sufficiency of negative charge on the right, so sulfate ions go over the salt bridge and even out the charges. And that's the way you complete the circuit. And that is a similar kind of thing to what is going on in the dry cell battery. But there's a question. Why does this reaction work? The zinc plus the copper ion producing zinc ion plus copper. But when you try this one, putting copper into the zinc ion, you get no reaction. Well, there's a chart that you need. And you're going to find it in any textbook, and you're going to find an abbreviated chart in this note guide. It's a table of standard electrode potentials at 25 degrees Celsius. So turn to it either in this note guide or in a textbook. Just pause this video and find it, and have it available as we go through and do this next part. Here is the table of standard reduction potentials. I greatly reduced the size of this table so I could get it on the screen and talk to you a little bit about it. It's written as standard reduction potentials, so things are written in order of their ability to gain electrons. And fluorine has the greatest tendency to gain electrons. It is, after all, the most electronegative element. And when fluorine gains electrons and becomes the fluoride ion in an aqueous media, it generates, or it produces, 2.9 volts. Everything else below it, everything else is of a lesser ability to act in that manner. This is your strongest oxidizing agent. That's fluorine. Everything else on this side, when it reacts this way, is behaving as an oxidizing agent, but is weaker than fluorine. Fluorine can force anything below it and on the right over here, anything below it and on the right, to react. It will take the electrons away. For example, you put fluorine with gold. The gold will lose electrons and become a gold ion. You put fluorine with bromide ions. Fluorine will take the electrons and drive bromine the other way. Kind of get a handle on how it works? Something up on the left will react with something down on the right. Now I want you to look at this right here. This one that is 0 is your hydrogen electrode. It's hydrogen and platinum. And it has a voltage of 0. Why do we say that? We say that because we had to have a standard to use. So we set this up as our standard. And everything above it has a positive voltage, and everything below it has a negative voltage. Now, where is your strongest reducing agent? And the answer to that is, it's down here, it's over here, right here. Yeah, that one right there is your strongest reducing agent. I'll explain a little bit more about how this works, and I will develop it a little bit more in the next few slides. I want you to look up some half reactions in the table that is either in the back of your note guide or in your textbook. Here's the first one. Cuprous ion AQ. Cuprous ion in solution plus 2 electrons giving you copper. Now look up the voltage. What do you get? Jot it down. This is what I get, plus about 0.34 volts. I've rounded off some. Now that's one of them. Now I want you to look up zinc solid forming the zinc ion in solution plus 2 electrons. What is that voltage? Now look at the way I've written it. The copper half cell we wrote gaining electrons. The zinc half cell we write losing electrons, so you've got to look it up on the other side of the column. And when you do, you've got to reverse the charge on the voltage, and you'll find it's going to be plus 0.76. Therefore, when you add up these two reactions and their voltages, you're going to get zinc metal reacting with copper ion, giving you zinc ion plus copper metal, and the voltage is going to be 1.10 volts. Anytime you can add the half cell potentials and get a positive voltage, that reaction is going to occur spontaneously. If you add up two half cells and get a negative voltage, then you have to input power to get the reaction to go that way. It's spontaneous in the other direction. What if we have these two reduction half cells? We have the ferric ion in aqueous gaining electrons producing the aqueous ferrous ion, and the voltage is 0.77 volts. And the bromine gains 2 electrons, forms 2 bromide ions, aqueous, and that voltage is 1.07 volts. Now, look at these. I've written them both as if they're gaining electrons. One will have to gain, one will have to lose. But which way do you write it? Well, let's look. Is it this way? Well, is this the way it will go spontaneously? Well, if we take the ferric ion plus electrons giving us the ferrous ion, and the bromide ion giving us bromine and 2 electrons, then our net voltage is negative. Do you see that? We had to change the sign on the bromine half cell because we wrote it in the other direction. So this isn't going to work. But what about this? What if we write the ferrous ion with bromine producing the ferric ion and 2 bromide ions, and we add up the voltages of that, and it's plus 0.30 volts. Now that is the reaction that will go spontaneously. Do you see how this works? We will do a much more extensive treatment on this in the second half of this course, but there's some things we need to address here to give you some good background. Which half cell has the greatest reduction potential? And that's this one right here. And since it has the greatest reduction potential, then it's the one that's going to gain the electrons. The order of the half cells, and this is important, the order of those half cells. How do we devise that whole table anyway? The order of the half cells becomes bromine plus 2 electrons producing the bromide ion, and the ferric ion plus an electron producing the ferrous ion. And when you put the two together, this one will go that way, and that one will go this way. And that's how you can add them up and get a complete reaction with a positive voltage. Consider this reaction. We have chloride ion reacting with permanganate, giving us the manganese ion and chlorine. Now here are the half cells that we get. Here are the half cells. We write them, remember, gaining electrons. So we write chlorine plus 2 electrons, giving us chloride ion, and permanganate plus 5 electrons, giving us the manganese ion. Now, which one has the greater reduction potential? Well, which one goes the way it's written? Look at your equation. That's what happened. Which one then is the higher one? This is the way in which they should be written. Permanganate plus 5 electrons. The permanganate gains 5 electrons easier than the chlorine gains 2 electrons. That's how we get their positions in the table. Imagine the hours chemists spent putting things together and seeing what would work and what wouldn't to try to come up with these kinds of things. Try this series. We have iodide ion reacting with bromine, producing bromide ion plus iodine. That's what we observe. That's the reaction that occurs. Now there are two half cells involved. Let's put them in order of reduction potential. Here they are. Iodine gains 2 electrons, producing the iodide ion. Bromine gains 2 electrons, producing the bromide ion. Now which one is going to go that way? Which one is going to gain the electrons? Well, you look at the reaction and you say, the bromine is going to gain the electrons. Sure, the bromine has the greater reduction potential. So it belongs on top. Look at this series of reactions. Now here are 4. Let's see if you can do them. We have 2 iodide ions plus bromine producing bromide ion plus iodine. That's one reaction. Then when we put the iodide ion with the ferric ion, we get iodine and the ferrous ion. When we put the bromide ion with the ferric ion, we don't get a reaction at all. And when we put the cuprous ion with iodine, we get the cupric ion plus iodide ion. Now, I want you to place these half cells in order of reduction potential, from the greatest reduction potential to the lowest reduction potential. Pause this presentation while you work, and let's get it in there. And here are the half cells you're dealing with. You're dealing with Cu plus 2, iodine, bromine, and the ferrous ion. Now pause this presentation and take those half cells, and based on those 4 equations, put them in the proper order. Then bring the program back on, and I will show you what I did. Here's the proper order. Bromine plus 2 electrons producing bromide ions. The ferric ion plus an electron producing the ferrous ion. Iodine plus 2 electrons giving you the iodide ion. And copper plus 2 plus an electron giving you the cuprous ion. Now, got it? Do you see why it's that way? This is what you should have come up with. Now, use that series right there, that reduction potential series, and predict these reactions. Predict this one. If I were to put ferric ion with the cuprous ion, would I get a reaction? Yes, I would produce the ferrous ion and the cuprous ion. If I were to put the cupric ion with the bromide ion, would I get a reaction? And the answer is no, I would not. As a final question to ask to see if you understand kind of what's going on, is either of these two compounds stable? Ferric iodide or ferric bromide, is either one of those stable? Are both stable? Is neither stable? Look at your reduction potentials and see if you can figure it out. Remember, something will gain electrons and something will lose electrons. You may pause this if you want to think about it. This one will not be stable. It will not be stable because iodide is going to lose the electrons to iron. This one is stable because the bromide ion cannot lose electrons or will not lose electrons to the ion. You got the idea? There is much more to be discussed regarding oxidation reduction reactions or electrochemistry. We're going to greatly extend these topics into talking about work and free energy related to cell potentials. We're going to talk about the relationship between cell potential and concentrations of solutions. We're going to talk about corrosion and electrolysis and practical applications of these concepts, such as applications in the evolving energies fields. Yes, there is much more to be done, but we're going to hold that until the second semester of this course, College Chemistry 2. This is not the end of the topic on oxidation reduction, but we will cover more relative to this in the next course. In this unit, we talked about some important terms. We assigned oxidation numbers. Remember how to do that, and you need to know your basic oxidation numbers. We balanced oxidation reduction reactions by the half-cell method and by the oxidation number method. We gave some examples of stoichiometry relative to oxidation reduction, and we spent some time talking about oxidizing agents and reducing agents, and what kinds of compounds or elements or ions could be each of these. And we wrapped up on the all-important topic of voltaic cells. A better way to teach and learn chemistry.